Welcome to Module 3 of Steam Power Part 1. In Chapter 8 of your textbook, you will find vapor power cycles. So in this section, we are going to cover how a steam power plant operates. This is in section 9.1, and the Rankine cycle that models a steam power plant. A manual solution of a Rankine cycle problem and its verification using a test calc will be covered in a separate module, and the rest of the topics will be covered in yet another module. The prereq for this chapter, for this section, is Chapter 4 review, especially problems involving PC model. We begin with an animation, a screenshot of an animation, 9A steam power plant. Well, let's start with the central part of the cycle. So state 1 is where we have steam at very high pressure and high temperature flowing into the turbine. Once we complete the cycle, you will understand how we generate the steam. But let's assume at state 1, we have steam at a very high pressure, let's say 1000 kPa, and high temperature, let's say 600 degrees Celsius. Superheated steam is available. It enters the turbine, expands through it, and produces turbine power. The turbine power that is produced, part of it goes back to the pump, and the rest goes to the generator, an electrical subsystem to produce electric power, which is the primary purpose of a steam power plant. The steam that comes out of the turbine is at a much lower pressure, much lower temperature, and then it is cooled in the condenser. What happens? Condenser is basically a heat exchanger. The steam, hot steam, passes through the condenser and is cooled by water coming from a cooling tower or a river or a lake or an ocean, and it recirculates, cooling, taking heat out of the steam. What happens to the steam as it passes to the condenser? It condenses to a liquid at state 3. And that's why this heat exchanger is called condenser, because vapor is condensing into liquid. So at state 3, we have liquid again, liquid which is pumped up to a very, very high pressure. It is the pump that makes the water go around this cycle. So the pump raises the pressure back to a very high pressure, and as the water passes to the boiler, it gets the heat from this furnace or a nuclear power plant. In the case of a nuclear power plant, fuel rods, or in case of a coal burning power plant, coal burning in this area. Natural gas power plant, there will be natural gas or methane burning here. In any way, the supply of heat comes in to the boiler, making the water boil and becomes superheated at state 1, and that kind of completes the cycle. Well, one thing to note is that if somebody says, how does this power plant work? And many people may say, at first thought that, oh, because in the boiler you are adding heat, the pressure is increasing here. That's nothing can be further from the truth. Whether you add heat or subtract heat, when there is a flow, generally pressure will decrease. Newton's law will dictate that, because for a flow to go forward, the net force will be 0 or positive in that direction. So the only way it's possible is pressure decreases, because after all there will be some friction inside the boiler. So from 4 to 1, in reality pressure will decrease, but ideally speaking, in an ideal boiler we can assume the pressure to remain the same. So from state 4 to 1, pressure remains the same. So in other words, the pump raises the pressure from 2000 kPa, and look, at the turbine exit the pressure is much lower. Let's say, just take some arbitrary number, let's say it's so low like 10 kPa. The condenser, where the heat is lost, again the pressure probably slightly decreases, but ideally we'll assume the condenser is frictionless, so at the condenser exit the pressure is still 10 kPa. So the pump raises the pressure from 10 kPa to 1000 kPa, and the turbine loses the pressure from 1000 to 10 kPa. The question is, how in the world the turbine produces more work than the pump? The answer lies, if you recall from our discussion in chapter 4 review, that in an internally reversible device, the work is proportional to integral VdP. So the pressure difference, the limit of the pressure is same for the compressor, for the pump and the turbine, and the mass flow rate is the same too. However, if you look at the specific volume of the fluid passing through the turbine versus the fluid passing through the pump, obviously turbine is handling superheated vapor, so the V inside the turbine is way higher than V inside the pump. Inside the pump it's pure liquid. There's almost a factor of 1000 difference between density of superheated steam and liquid water. That's why turbine power is going to be way bigger than pump power. If you recall, in our gas turbine analysis, we realized that the turbine produces more work than the compressor because turbine handles air at a higher temperature than the compressor, which handles air at a lower temperature. Just the temperature difference there created the difference between specific volume. Imagine in the case of a Rankine cycle. In the case of this power plant, the difference is created by condensation. Liquid is so much denser than the vapor. That's why the turbine power is way, way higher than pump power. And their ratio, called the backwork ratio, is very, very small compared to a Brayton cycle. Well, so this is at the heart of why a steam power plant, why it works so well. Well, to model a steam power plant, we use what is known as a Rankine cycle. Again, this is an excerpt from an animation of the Rankine cycle. So what happens in an ideal Rankine cycle? Let's start from an arbitrary state, say state 1. As we already mentioned, suppose steam is at 1000 kPa, 600 degrees Celsius. So how do you represent the state on a TS diagram? Recall from your PC model knowledge, in a TS diagram there is a dome shape that separates superheated vapor phase from subcooled liquid phase, and inside the dome we have the mixture phase, which is liquid and vapor coexisting together. A constant pressure line on a TS diagram looks something like this, a knee-shaped graph if you recall, with saturated liquid and saturated vapor represented by F and G states. So if this is the 1000 kPa line, a superheated vapor point state 1 would be somewhere up there in the superheated vapor region. As the steam expands to the turbine, we know entropy remains constant in an ideal turbine. So as you can see, from state 1 we reach state 2. Well, state 2 could be, if state 1 was higher up there, state 2 could be superheated too, but in this diagram state 2 seems like is in the mixture zone, liquid plus vapor. So what happens from 2 to 3? The steam that comes out of the turbine is now cooled in the condenser, and we lose heat Q dot out here into the circulating water, and as heat is lost, the steam start condensing, and at the exit it becomes saturated liquid. So state 3 is a F state, saturated liquid state in an ideal Rankine cycle. So from state 3, of course the pressure doesn't change because condensation is just opposite of boiling, going in the reverse direction. So temperature doesn't change, and at state 3 we raise the pressure of the liquid using a pump, and it's an isentropic pump. So from 3 to 4 we are adding pump work, Of course, a little part of the turbine work is fed back to the pump, and the rest of the network is producing the electricity. From 4 to 1 in the boiler, we are adding heat, Q dot in, and as you can see, it's a constant pressure line. Heat is added. Liquid water goes up here. Over here, it becomes saturated liquid. Then more heat is added. Boiling takes place at a constant temperature. We reach saturated vapor point, and then we keep adding heat until we reach the maximum temperature, which in this case we assume to be 600 degrees Celsius. So this is a 10 kPa line we assumed, and 1000 kPa line. So there are two different pressures. On the low pressure side, we have 10 kPa here between state on this part of the cycle, and on the rest of the cycle we have 1000 kPa where after the pump. So as you can see, the net area that is enclosed is proportional to the net power. To explain that in terms of formulas, recall that in any cycle, net work and net heat are equal, and in case of the Rankine cycle, you can show that W dot times m dot times W net equals W dot net, and m dot times Q net equals Q dot net. In other words, the net power, the net work and net heat of the cycle inside the TS diagram, which are equal, times mass flow rate, is the net power. So the thermal efficiency of the Rankine cycle, or for that matter any cycle, is given by this. We have done that a million times. So this is some overall formulas, and the back work ratio is given by W dot pump, W dot turbine. Also, you can write W dot net, turbine minus pump, and Q dot net, of course, is Q dot in minus Q dot out. Okay, let's now analyze individual devices in the cycle, many of which are familiar to you already. So the turbine work, W dot T, can be, without using energy equation, you can directly write. We know how much energy is entering here, m dot H1, how much energy is coming here, and the difference between the two must be W dot T. And if we want to know what happens as far as entropy is concerned, we recognize entropy that comes in, entropy that comes out. By mass, by heat, there is no entropy that crosses the boundary, and there is no friction in an ideal turbine. Steady state, this goes to 0. So therefore, S1 equals S2. If we have to draw this on a TS diagram, we understand that in case this is my state 1 superheated vapor, and if the turbine operates between this pressure and this lower pressure, so this will be state 2. So let's go work on the next device, which is the condenser. Okay, in the condenser what we got is heat loss, heat rejection, Q dot out, again a positive quantity here, Q dot out. The energy that goes in is m dot times H2 with the mass, m dot times H3 is coming out, so Q dot out must be what goes in minus what comes out. On a TS diagram, we already showed, but let me just do it again. So suppose this is my exit state 3, 2, then by definition of the Rankine cycle, ideal Rankine cycle, state 3 is going to be saturated, the F state. So this is the heat transfer, Q dot out. This is proportional to this area. And now we have the pump. In pump, we need work. Again, following the same logic, the pump work is given by what is m dot times H4 minus H3, the bigger enthalpy minus the smaller one. You can show, just like the turbine, S3 is entering, m dot S4 is coming out. There is no heat transfer. This term is not there. There is no friction, no entropy generation. Steady state, that's why it's isentropic. And if we draw the TS diagram again and do the two different pressure line, so if this is our state 3, state 4 is isentropic. One point to mention here, that even though 3 and 4 I'm separating, when we compute the states, you will see that 4 is awfully close to 3. You cannot even separate them. They're so close to each other. So this separation is typically exaggerated in any diagram, in any TS diagram, to show that pressure is increased isentropically. Now the last device, which is the boiler, where heat is added from the hot thermal energy reservoir, Q dot in, and again following the logic that the mass flow is carrying this amount of energy, transporting this amount of energy out. So therefore Q in must be, m dot H1 must be much bigger than m dot H4. And on a TS diagram, from state 4 to state 1, which is superheated, as heat is added, we can see we're going up to the water is heated to the temperature of boiling temperature, and as the boiling starts, temperature doesn't change. So this is our F state, this is our G state, and then we are superheating it to temperature 1. The area underneath is proportional to how much heat is added, which means the net area inside the cycle is therefore the net area therefore is equal to proportional to Q dot net, which is equal to W dot net. So now that we know how to analyze individual devices, we'll go solve a simple problem before we go and try to modify the Rankine cycle, try to understand how to influence its efficiency and net power.